Hi, I'm Christopherson. I'm from Intel. I'm going to be talking about virtualizing the PMU for the cloud, but really this should read as making perf usable in the KVM guest. Of note, the contributors here are the people from Intel that are actually doing the work. I'm just presenting, so all of the credit goes to those people. Agenda. So as mentioned, the goal of the project is to get the virtual PMU actually usable in the cloud. Today, if you go look at the vast majority, probably all cloud instances, you'll see that if you try and do anything remotely interesting with perf, you're going to get some event not supported. And this is because they don't expose the virtual PMU to their instances. The reasons for that are that in a KVM guest, you generally get inaccurate results, and we also don't currently have support for advanced features in KVM. So last branch records and event-based sampling, PEBS. Note today I'm just going to talk about optimizing the PMU and LBRs. For time, PEBS gets shoved off the end. So even though things aren't actually exposed, most vendors, most cloud vendors do have a strong interest in making the PMU usable in their cloud because customers want to be able to run perf on their workloads in the cloud. And also internally, we've gotten complaints from people at Intel saying, hey, on Hyper-V, I can do all this perf testing, and on KVM, it's basically useless. So strong incentive to make it actually usable. So what we've been working on at Intel is to reduce the overhead so that you actually get some accurate results, and then to also add LBR and PEBS virtualization in KVM. So a quick crash course on PMU. Each logical CPU has its own PMU block. At the heart of the PMU is a set of general purpose counters. So they vary by microarchitecture. But you'll have 8+ general purpose counters that can be configured to support any supported event on the target hardware. So this can be things like counting the number of core cycles that you've been running unhalted, instructions retired, branches retired, branches missed, etc. There are also a set of fixed function counters, and these are fixed in the sense that the event that they count is hardwired into the counter itself. The advantage of these is there's less work to do to get them programmed and running. The counters themselves aren't all that useful. Simply counting events isn't going to provide you any information about where an event occurred. So if you're tracking how many branches have I missed, it's not very useful on its own to know that you missed n number of branches because you don't know where your branches are being missed. So to that end, you have interrupts that can be generated. So performance monitoring interrupts, or PMIs, can be generated after n number of events, which is configurable by software. The reason why you want to have a configurable number of events that you generate an interrupt after is so that you can balance between the overhead you incur on your workload and your accuracy of sampling. So if you configure to generate events really frequently, you'll get super high accuracy, but your workload performance will tank probably to the point where you can't even make forward progress. Because of this trade-off, sampling individual IPs isn't going to be a solution. And so for some cases where you want to, say, get a stack trace without frame pointers, or you want to analyze which branches are hot, which branches are cold, you need essentially better precision of your IP. So that's where last branch records come in. LBRs are essentially a stack of MSRs that capture the to and from addresses whenever you take a branch. And so this way, after when you take your sample, you can read out all the LBRs and see your last 32 or whatever branches that you've taken. And so you kind of batch them all together and take fewer interrupts, but still get some very high accuracy. So if we take a look at what how this plays out in native Linux, you run the perf utility to take a look at branch misses. And sorry, this is in the context of just general PMU usage. That calls into the user space perf utility here. makes a syscall into the perf subsystem. So we're associated with this test program thread. At this point, the perf subsystem creates a perf event. The perf event is used to store config data and state data about that event. It's usually associated with one or more of the PMU counters. And I'll say why it's not directly tied to a PMU counter in just a second. And probably the most important part for this discussion is that a perf event is a schedulable entity. And so this means that when you're scheduling that the task onto a physical or logical CPU, the perf subsystem is also going to run its own scheduling. And the reason for doing this is that there may be multiple sources of perf events in the system. So not just this single perf running the test program, but you can have other things that attach perf events to this. So scheduling means that when we schedule that thread onto a logical CPU, the PMU, the perf subsystem also schedules the perf events onto the PMU. And so this kind of lets you essentially overcommit your perf events. You don't have to have a priori knowledge of how many PMU counters you have and which events need which counters, et cetera. You can do this all at schedule time, and the ones that are lower priority kind of get tossed away. And this is also why it's very difficult for virtualization on Linux, because how do you balance the priority between host and KVM? You can't just give all of your counters to KVM, then you can't do anything in the host. And these are all MSRs, so when you're programming up the PMU, you're just doing MSR reads and writes. The interrupts that occur when you trigger n events or whatever come back into the perf subsystem, and that gets filtered back out to user space. If we take this up to a KVM guest, so Linux guest running on KVM, doing the same test program, same perf event gets created in the guest. This time when we finally do that MSR write, it gets intercepted by KVM, so it's a virtual MSR access. KVM then makes function calls into the perf subsystem, but we're going through the full perf stack. So this creates the perf event then gets scheduled, gets loaded into the actual PMU, and then we generate the PMIs and we come back, get callbacks into KVM, and inject the virtual PMI into the KVM guest. But this is really slow because the perf stack is heavy. So going through the existing perf stack and this naive implementation, not including the PMI, just to program a PMU counter from the guest, takes us about a little over 2.5 milliseconds. So to improve the performance, so 2.5 milliseconds is an eternity, and it's why the results are very inaccurate. We still have the same basic environment. We still trap on the MSR accesses to the PMU. We still have to do some function calls into the perf subsystem. We still create the perf event, but we're not going through the full perf stack. And we don't rely on the perf scheduling. Instead, we kind of steal the MSR and allow KVM to program it directly. And so then KVM can program the PMU whenever I'm jumping ahead here. We still do the PMIs through everything else. But by allowing the KVM to do its own programming in the PMU, we avoid all the overhead. And then whenever the guest is updating it, because it already essentially owns that hardware MSR, we can drop that 2.5 milliseconds down to little under 700 nanoseconds. The caveat to this approach is that the perf maintainers weren't exactly thrilled about KVM stealing counters away from the host subsystem. So this got knacked pretty quickly, but it's a good way to show how much room for improvement we have. So we're at 2.5 milliseconds, which is awful, but kind of pie in the sky, we can get down close to this sub-microsecond range. For LBR virtualization, logically, the LBR MSRs, they're part of the PMU, and so accordingly, they're part of the virtual PMU and KVM. When we start running the vCPU, there's really no data attached to the vCPU for the LBRs at this point. At some point in time, the guest is going to create a test program with a perf event associated with it, and at this point, it does a MSR write to enable the LBRs. We intercept that in KVM, note that LBRs have been enabled, We still create a perf event. The reason we do this is to aid in the context switching. Because we have all these MSRs that have IP addresses in them, we don't want to expose those to the guest. So we need to context switch when we're transitioning between guest and host. When we enable the LBRs and we context switch them, we give pass-through access into the guest. So when the guest gets a perf event associated with an LBR and gets that PMI, it can go and read out the MSRs directly. And then when we schedule out the vCPU, we obviously remove access and we context switch back the host state, and then rinse and repeat. Eventually, the guest is going to tear down its PMU event for the LBR programming, so it's like essentially that perf stops running. It comes through, does the MSR access, so this enable is still intercepted. It's to the debug control MSR. On the host side, we disable the LBR pass-through, but we don't actually disable the perf event at this time. So KVM waits until a full time slice goes through, and there are no LBR accesses. Only after that, so we go through a full time slice, we haven't had any LBR accesses that trap out to KVM because we're no longer intercepting them. And then at that point, once we've gone through that full cycle, we tear down the perf event. The reason for doing this is, as mentioned before, the perf subsystem going through all that is pretty heavy and slow. And it's not uncommon to temporarily disable LBRs in the kernel. So if the guest temporarily disables LBRs and then re-enables them, we don't want to have to go through that reprogramming. We can just say, oh yeah, you already have a perf event. We can just re-enable the LBR pass-through and give the guest access to the LBRs without having to go through the perf subsystem again. So results, just the test environment for reference if you want to play around with this. So for the optimizations, comparing the latency before and after, just for the MSR update, so programming the PMU counters, we got 3,500. Again, this is optimal, absolute best case scenario, essentially. And then for the PMI latency, we also take it down by about 900x. So the effects of that reduction in latency you can observe very easily with some basic analysis in the guest. So running a perf to track branch misses, we take a look at the host to get a reference. So in the host here, you have the percentage of branches missed out of total in the process, the binary, and then which function. So ideally, when you run in the guest, you're going to get very similar results, so that you can show that regardless of whether I'm running on the host or the guest, I still get the same tracing information essentially in the same perf result. Running without optimization, you can see that the results are effectively garbage. The programming is so slow that all of the PMIs and all of the events that we're sampling end up in the kernel, and we don't actually get any useful information about our guest workload. And it's actually so slow to the point that this run was gathered just by killing the process because it was just stalled indefinitely effectively. With optimization, we end up with results that are basically identical to what we see in host, so showing that by reducing that latency, you can actually make perf usable in the guest. Similar example with LBRs, run on the host to get a reference, and then run the same workload in the guest and observe that they produce similar results. Don't worry about the absolute values in the columns here. It's a somewhat suboptimal view of what the call graph would look like, but it's better for comparison. So where we're at, so I mentioned that the full optimization was kind of shot down by the perf maintainers. We're working on intermediate steps right now to improve and reduce that overhead. So there's lots of things to make the programming from KVM into the perf subsystem a lot less naive. And we don't need the full, essentially, syscall flow that exists today. And then LBRs and PEBs have both also been posted upstream for inclusion into KVM. So all three of those are still live. They're under review right now. We would love to get eyes on this and input from people that are actually planning on using it as well. For the future work, so obviously we're going to continue upstreaming the patches and then continue working on optimizing the PMU. And probably in parallel to that, we'll start working on supporting additional versions of the PMU. So Intel has, I forget it, as of Nehalem or so, what it calls an architectural PMU. And so this is something where the core tenets of the PMU won't change from microarchitecture to microarchitecture, but there are new versions of it. So the most recent versions add new events, so we can work on exposing more events to the KVM guests. Thank you.
Can you explain a bit more about how the partitioning of the PMU counters between the host and the guest looks like? Like, when do you decide to steal a PMU counter? How much do you take?
So that's not, the odds of that ever actually getting upstream are minor, very, very small.
Okay.
Essentially, my understanding of what is being done is when the guest requests a counter, we give it to him.
But how much, does it depend on how much counters you expose by the CPU ID leaf?
I don't know the details of how that particular implementation was going.
Okay.
And I could, that's all things that I'm sure you can negotiate once we try and upstream of, okay, if we get to the point where we've got 256 counters in hardware, which probably isn't going to happen, but let's say we got there, then at that point, we can probably go to the perf subsystem people and be like, hey, you only need 240 of those. Can we have 16 to give to the guests, something like that?
I'm wondering about whether if we use this approach, and for example, at the moment that the guest enables PMU, you still the amount of exposed PMU counters that was exposed to him in the CPU ID, then maybe it was useful from user space to be able to control how many PMU counters you expose to the guest.
It's not just user space, though, because you can have perf events that are associated with things that don't come directly from unprivileged users.
Oh, I see. Okay.
That's the crux of the problem. If this was purely a user space thing where user space could opt in and say, I'm not going to use perf at all, then yeah, we could hand everything over, but it doesn't work that way.
Okay, I see. Thanks.
Thank you.
That looks like really nice work, and the numbers looked very impressive. Also, the fidelity of the results when you compared it to what you saw on the host. I assume those numbers are for that patch set that you said was knacked.
Yes.
Can you shed some light on what you expect that intermediate patch set to give you in that respect? Like, would you lose a lot, or?
Just speaking from general KVM experience, there's no reason that you should have, the 3000x overhead. Like, that's absolutely ridiculous. There's like 2x maybe, 10x maybe, but I would expect no worse than that. So that's why I say a few microseconds, and I'm guessing you still have that decent fidelity.
Right, so you expect that you would be more in that area, even with your let's say, middle-of-the-road approach that you could get upstream.
I don't know that we're going to get there with this intermediate patch set. I'm expecting this will be a, rather than go for the gold right out of the bat, I think we're going to have some intermediate patches and multiple patch series to get us to the point where we really get that high fidelity that we're looking for.
All right, thanks.
Yeah.
So when you do the LBR pass-through, is there any security concerns with that there might be something in the LBR that the guest was not supposed to see?
No, because we're context switching them. So when we go into the guest, we purge the values that were there from the host. And kind of by definition, once you're in the guest, it's just going to see guest IP addresses. It's not going to see physical addresses, for example, or we're not going to leak that type of information.
Hi, a question related to a feature called as memory partitioning and monitoring, MPAM. That is what we call on the ARM world. So I think Intel has got a similar feature for partitioning the caches and other part of the system, right? And probably you can have a different counters for each of such partitioned. They have the different partition ID. So my question is there any work which is involved, first of all, at the host level and at the virtualization layer as well, to take care of this partitioning and related counters?
You're talking about things like Intel's resource director
Exactly.
technology.
RTD, yes, that's the one.
You're specifically asking if we are
plan
passing
to-
that through to the guest or using it in a virtualization context?
In a vCPU context, suppose you have to
So
do
the way resource director technology is implemented in the kernel, it's similar to C groups. It's not actually C groups, but the concepts are the same, and that means you're applying it to essentially the QEMU process and the tasks owned by QEMU. So there's no reason that you wouldn't be able to use it to assign resources to vCPUs. So it should just work as is, and if it doesn't, we need to work on that.
Yeah, sure. Thanks.
Yeah.
If there are no other questions, thank you.